Imagine this. You're there in the flight deck, big airliner just broken through the clouds, and there's the runway stretching out below you. But it's not one of those perfect clear days. You hear the report. Runway wet, patches of standing water, bit of a crosswind. And as those wheels make contact, that gentle bump, you feel the massive weight settle. In that moment, this landing isn't just routine. It's a total reliance on every single system, every piece of engineering working perfectly to bring this huge machine and everyone on board safely to a stop. Today, we're doing a deep dive into one of those absolutely critical systems. It's a really remarkable feat of engineering, actually. It takes situations that could be pretty challenging, maybe even dangerous, and turns them into manageable, controlled operations. We're talking about reverse thrust in gas turbines. That powerful roar you often hear right after touchdown? That's it. Seems simple, maybe, but it's incredibly complex and adds this vital layer of safety and control. And for you, especially if you're deep in study mode, prepping for those ATPL theory exams, well, this deep dive is absolutely for you. We've tailored it with that in mind. Our mission here is to really unpack the mechanics, how it operates, and, crucially, the safety systems involved with reverse thrust. We're going to pull out the key knowledge, highlight the stuff you absolutely need to know for those exam questions. The goal is you walk away not just, informed, but really understanding this vital aircraft component, ready to nail those questions.
That's exactly the plan. And to help us navigate this, we're drawing from some really insightful material, specifically excerpts from Gas Turbines, The Mechanics of Reverse Thrust. It lays things out very clearly, very comprehensively. So we'll be using this as our guide, pulling out those golden nuggets of information that are directly relevant to your ATPL studies and, honestly, to being a knowledgeable pilot.
Okay, great. So let's get into it. Given how advanced modern aircraft brakes are, they're pretty sophisticated, right? So what makes reverse thrust still so essential? How does it really change the game for a pilot during that critical landing phase?
That's a fantastic starting point because it gets right to the heart of why reverse thrust exists. You're right, modern braking systems are incredible. We're talking multi-disc carbon brakes, anti-skid units, auto brake systems. They're designed for immense stopping power, but even with all that sophistication, they fundamentally rely on one thing: friction between the tires and the runway. Now think about a runway that's, say, soaked after a downpour. Or worse, it's got patches of ice, or maybe slush or snow. In those conditions, that vital friction, the coefficient of friction, just plummets. So that amazing braking system suddenly becomes much less effective. It can even become a liability, making it harder to control the aircraft and dramatically increasing the stopping distance.
Right, so the brakes are only as good as the grip they can get, and that's where reverse thrust steps in. Our source calls it a monumental improvement. That sounds pretty significant.
It absolutely is. Monumental is the right word. It fundamentally changes the equation. Landing on a slippery, contaminated runway, maybe with a trippy crosswind, that goes from being a potentially, terrifying scenario to something a competent pilot can manage safely. And the real magic, something really key for you to grasp for your exams, is how it works. It provides frictionless deceleration. It's an aerodynamic force. So when the runway surface is slick and the wheels can't get good grip, reverse thrust cuts through that limitation. It doesn't just help the brakes, it provides a completely independent, powerful braking force. It really does change the game.
Frictionless deceleration. I like that. So the actual difference in stopping distance, is it noticeable or truly significant?
Oh, it's significant. The source says the difference is quite marked, and that's almost an understatement sometimes. We're not just shaving off a few feet here. It can be a dramatic reduction in the total landing distance needed. And that directly translates into much bigger safety margins, more runway left over, more time to react, especially when conditions are bad. It's like having an extra safety net built right into the engines.
Okay, so when exactly is it deployed? Is it automatic or pilot selected?
It's pilot selected, typically right after the main wheels are firmly on the ground. That weight on wheels signal is crucial. It's an interlock we'll talk more about later, preventing deployment in the air. And it doesn't work in isolation.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.